Recall from the previous lesson that energy comes in many different forms. Useful energy, energy that can be harnessed, is known as mechanical energy, whereas energy that's been degraded and can no longer be harnessed is thought of as wasted energy, which often appears in the form of thermal energy. So there are a couple major categories of mechanical energy. Energy of motion is called kinetic energy, and stored energy waiting to be released and converted into kinetic energy is referred to as potential energy. Now we know from the previous chapter of study how we calculate kinetic energy. It's energy of motion, so therefore it depends on how fast an object is moving. In fact, it depends largely on how fast. Velocity is squared in the equation for calculating kinetic energy. So a doubling of an object's velocity is a quadrupling of its kinetic energy. For potential energy, there are several forms. There's gravitational potential energy, elastic potential energy. Chemical potential energy, we won't discuss at great length in this unit of study, nor will we discuss electrical potential energy or any other forms. So we want to focus in this unit of study on potential energy in the form of gravitational and elastic potential energy. And in this lesson in particular, we're going to focus on gravitational potential energy. So gravitational potential energy is symbolized as capital U subscript G, and elastic potential energy, capital U subscript S. All these forms of energy, whether it's thermal, kinetic, or potential, are all measured in joules. And whether it's kinetic energy, thermal energy, or potential energy, it represents a scalar quantity. There's no direction associated with energy. In other words, energy is certainly not a vector quantity. Okay, so let's come up with an equation for gravitational potential energy. And we'll start by thinking about how much work is done when an object of mass m falls straight down, ultimately hits the ground, and falls through a displacement delta y. Well, the work done by gravity, like all work, is a vector dot product of force with displacement, meaning it's equal to the force of gravity multiplied by the magnitude of the displacement multiplied by the cosine of the angle between those two vectors. Well, the gravity vector in this case points straight down, and of course the displacement also points straight down. So this becomes cosine of 0 degrees, which is equal to 1. So very simply put, the work done by gravity is equal to mg delta y. In most cases, we'll rename delta y as h. After all, it represents some height, a vertical displacement. So the work done by gravity, we can say, is mgh. Okay, so what is the gravitational potential energy? Let's come back to that. I want to consider the amount of work that's done by gravity in this case. Now let's say it's the same amount of vertical displacement as it was in the previous problem, but instead of falling straight down, our block of mass m slides down a frictionless surface. Obviously, it's going to gain speed as it loses height. In other words, as the gravitational potential energy goes down, the kinetic energy goes up. So the work done by gravity in this case, well, once again, it's due to the force of gravity, mg. There's a displacement, delta s, and there's an angle between those vectors that we can call theta. Now you should recognize that this angle theta is complementary to this angle phi. Okay, so work done is the force of gravity dot product with the displacement, which means the work done by gravity is equal to mg times delta S times cosine theta. However, because theta and phi are complements to one another, in other words, theta plus phi equals 90 degrees, or better yet, theta equals 90 minus phi, then we can say the work done by gravity is equal to mg delta S sine of phi, right? The cosine of theta and the sine of phi must be equal since those two angles add up to 90 degrees. But what is delta S sine phi? Well, if you look at this right triangle, delta S is the hypotenuse. The angle phi is opposite the side labeled as delta y. So in fact, delta S sine of phi is nothing more than delta y. So the work done by gravity in this case is equal to mg delta y. And as we often do, instead of calling it delta y, we call it h for height. So the work done by gravity is mgh. Now does that look familiar? Of course. What is the change in gravitational potential energy in this case? Well, we know what the change in kinetic energy is because there was no friction and because normal force is perpendicular to the displacement. No work was done by friction. No work was done by the normal force. Now, for two different reasons, right? No work was done by friction simply because there is no frictional force. There is a normal force, but there's no work done by it because it's perpendicular to the displacement. So all I'm trying to suggest is that gravity was the one and only force. So not only is mgh the work done by gravity, but it's also the net amount of work. But net amount of work is always equal to change in kinetic energy. That's the very important work kinetic energy theorem from our last unit of study. So if the loss of potential energy is the increase in kinetic energy, then it must follow that the change in gravitational potential energy is equal to negative the change in kinetic energy. As one goes down, the other goes up by the same amount. And so the change in gravitational potential energy is equal to negative mgh. So what would be the change in gravitational potential energy if instead the block was lifted to the top? Well, then it would be just the opposite. The change in gravitational potential energy would be positive mgh. In other words, as something goes higher and higher, the potential energy increases, and when something goes lower and lower, the potential energy decreases. In fact, in the first case, it's the same thing. Had we suggested the block was being lifted up to a height h, the change in gravitational potential energy would have been positive mgh, and by the way, the work done by gravity would have been negative mgh. In any case, this is a problem where we were imagining the block was falling. So the change in gravitational potential energy in that case is also equal to negative mgh. Could it be that if an object were to lose elevation in this manner by sliding down a quarter circular path, that the change in gravitational potential energy is also equal to negative mgh? Well, let's find out. A block of mass m has a force of gravity pulling straight down. Now, when our block gets to this position right here, the force of gravity still pulls straight down. Same as when it gets to the flat surface. The force of gravity always pulls straight down. But the instantaneous displacement vector, right? It's always displacing tangent to the path. So in the beginning, the displacement, and we'll break the displacement up into little bits. There's a little bit of displacement ds. There's another little bit ds, and another little bit ds. These are all little vectors. You know what we're going to do. We're going to break the path up into such small incremental bits that we'll imagine ds is approaching 0, or at least we'll take the limit as ds does so. So by the time the block gets to this position, the vector ds points in that direction, and once it reaches the flat ground, ds points in this direction. So the magnitude of the force is always the same, mg, and the length of our infinitesimally small ds vectors will always be the same, but the angle is always changing. Here, theta is equal to 0 degrees. ds and mg point in the same direction. Here, there's some angle theta, and in the end, theta is equal to 90 degrees. Well, the work done by gravity must be equal to, in this case, we have to integrate because the dot product is changing, right? Due to the fact that the angle is changing. So it's the dot product of force and incremental displacement, which means it's the integral of mg, the magnitude of the force, ds, the magnitude of the displacement, cosine theta, as a way to account for the vector dot product. Okay, so the work done by gravity is equal to, now let's see, what can we substitute for ds? We all know that the distance around a complete 360 degrees of a circle is known as the circumference, and that's equal to 2 pi multiplied by the radius. Now 2 pi is nothing more than the angular displacement associated with a full circle. Well, what about the case where an object displaces only the fraction of a circular path? What if you have a displacement delta s that's not all the way around? It's the same formula, it's just the angle is something other than 2 pi, but if you multiply the angle in radians times the radius, which is all we're doing in this equation, multiplying the angle, not in degrees, but in radians, times the radius, that gives us the displacement along the perimeter of the path. So this is the general formula for displacement along a circular path. Well, if we want to change it then from delta s to ds, that means ds is equal to d theta times r, or how do we call it, r d theta. So that's what we get to substitute for ds, r d theta. So the work done by gravity is the integral of mg r d theta times cosine theta. Oh, and what are our limits of integration? The m is constant, the g is constant, the r is constant. Clearly, theta is the variable, and we can see that in the initial case, theta is 0, and in the final case, theta is 90 degrees. Right? We're integrating from 0 to 90 degrees. Or if we want to keep it in radians, that's fine. We can say from 0 to pi over 2, whichever you prefer. So the work done by gravity is equal to, let's pull all the constants out, mgr times the integral from 0 to 90 degrees of cosine theta d theta. And the integral of cosine theta is just sine theta. So we get the work done by gravity is equal to mgr sine theta evaluated from 0 to 90 degrees. Well, the sine of 90 is 1. The sine of 0 is 0. So we find the work done by gravity is just mgr. And again, I think it was assumed we were taking the case where there is no coefficient of friction. So there's no work done by friction. There's never work done by the normal force. The normal force is always perpendicular to the displacement. So when the object is here, the normal force points that way, and the instantaneous displacement is perpendicular to that. Initially, the normal force points this way, and the displacement points straight down, right? So the normal force and the displacement are always 90 degrees apart, so there's never work done by normal force. So all we're trying to say now is that not only does mgr represent the work done by gravity, it also represents the net amount of work. but net amount of work is always equal to change in kinetic energy. And we can ask ourselves, where does the kinetic energy of this block come from as it slides across this level ground? It didn't have any kinetic energy here because it was released at a state of rest. So the increase in kinetic energy as it slides from point A to point B comes at the loss of gravitational potential energy. So if the gain in kinetic energy equals negative the change in gravitational potential energy, then our change in gravitational potential energy in this case is once again negative mgr. Now why negative? Because the object fell downward. Oh, and by the way, we notice we could label this as the radius of the circle, but couldn't we also label here the same thing, r? In other words, the radius is the same thing as the height. So once again, we find the work done by gravity is mgh, and the change in potential energy is negative mgh. Would you guess that an object of mass m that slides down this track and ultimately ends up at the bottom, provided this is a frictionless track, it ends up at the bottom moving with some velocity v, it has mass, therefore it has kinetic energy. Where did that kinetic energy come from? As gravitational potential energy decreased by virtue of losing altitude, the kinetic energy increased. And I think by now you probably have a guess what is the amount of work done by gravity in this case. I think you'd guess it's mgh. What's the change in gravitational potential energy? Negative mgh. So the outcome here is that work done by gravity is path independent. It doesn't matter whether the object falls straight down, slides down a ramp, follows a curved path, or follows any other random type path. If the displacement vertically is always h, even if the actual path is something other than h, right? All that matters is the amount of vertical displacement. And in every one of these cases, the vertical displacement, h, is the same. So change in gravitational potential energy is path independent. That's because gravity is a conservative force. Friction is not a conservative force. Air resistance is not a conservative force. Gravity is, and we'll explain more in another video lesson, but generally speaking, whenever you have conservative forces, the work done by conservative forces tends to be path independent. And in that case, the work done by the conservative force is always equal to negative the change in potential energy associated with that conservative force. Work done by gravity is always equal to negative the change in gravitational potential energy. And now it seems like we've derived an equation then for change in gravitational potential energy. It's equal to mg times change in vertical displacement. If you always set your reference level so that height equals 0 at the ultimate vertical landing point for the object, then we can say the initial gravitational potential energy is equal to mgh. However, gravitational potential energy is actually somewhat of an arbitrary value. Let's take, for example, a bowling ball hanging from the end of a rope, and it sits about 2 meters off the floor. And then you pull the bowling ball back some angle so that it's been lifted so that it's now 3 meters off the floor. How much gravitational potential energy does it have? Some people would say the gravitational potential energy is mg. Well, we always want to say it's mgh, right? When the object is right here, what value should we put in for h? Some people figure they should put in 3 meters as the value for h. However, as the bowling ball swings through this arc, it's never actually going to reach the floor. It's only going to reach this lowest elevation. So maybe we need to reset things and say that we don't think of h equals 0 at the floor. We should think of h equals 0 at the lowest point in the swing. Then in that case, we clearly wouldn't put in 3 meters as the value of h. We would put in the difference between 3 and 2 meters. In other words, we just put in 1 meter. But how about this? For people who are standing in this room looking at the bowling ball, those would be the two most obvious options, to either let h equal 0 at the floor or let h equal 0 at the low point in the swing. However, this could all be inside of a 2-story building. There could be somebody standing on the upper floor, and let's just imagine there's a hole in the floor. Now, when they look down, they're going to see that the bowling ball is actually somewhere below what they would probably think of a reference level, h equals 0, at the floor of the second story of this building. Then they would say that the potential energy when the ball is here is actually some negative value. I don't know. Let's say that this is a 5 meter tall second story. Okay, well then when the bowling ball is here, if this is 3 meters off the floor and this is 5 meters, then the bowling ball is negative 2 meters below this reference point. So this person would say the gravitational potential energy of the bowling ball is negative. A person who lets the reference level be 0 at the floor would say the gravitational potential energy is based on a height of 3 meters, or somebody who moves the reference level of 0 to this elevation would say there's a lesser amount of gravitational potential energy associated with only 1 meter. Well, they can't all be correct, right? What is the bowling ball's gravitational potential energy? It turns out gravitational potential energy is arbitrary and not very meaningful, but change in gravitational potential energy is very meaningful. In other words, no two people will agree on the value of an object's gravitational potential energy, but they will always agree on changes in potential energy. After all, let's consider this one more time. There's a 2-story building. The height of this floor is 5 meters. The bowling ball is 2 meters off the ground. When it's pulled to here, it's now 3 meters off the ground. So let's consider somebody who sets the reference level h equals 0 at the ground floor. Then they would say the initial gravitational potential energy of the bowling ball at point A is equal to mg times 3 meters. And they would say that the final gravitational potential energy when it reaches the low point in the swing here at point B is equal to mg times 2 meters. Okay, so the change in gravitational potential energy is going to be negative because it fell down, and in the end, it's just the gravitational potential energy at point B minus the gravitational potential energy at point A. If we factor out the mg, this is mg of 2 meters minus 3 meters, which just gives us mg times negative 1 meter. Let's consider the person who says, no, height equals 0 at the low point of the swing. Then their change in gravitational potential energy, which is the energy at point B minus the energy at point A, would be mg times what? 0 minus mg times -1. Okay, what about the person standing on the second floor looking through the hole in the ground? They would say change in gravitational potential energy is the energy at position B minus the energy at position A. And in this case, they would say it's mg. Now, when it's at point B, they would say that it's at a position of -3 meters. And when it's at position A, they would say it's at -2 meters. And so again, they get a value of mg times -1 meter. So, see what my point? No two people agree on gravitational potential energy because it's up to you to choose your reference system, your frame of reference whenever studying the motion of objects, and you can set height equal to 0 wherever you choose. But the change in gravitational potential energy as an object moves will always come out the same regardless of your choice of reference system. Thanks for watching.